In this unit, we're going to be talking about filters. We're going to start with our ideal filters, and then later on we're going to talk about passive filters and active filters. So first of all, we want to ask ourselves, what do we mean by filters? So everybody's probably familiar with some type of filter in their daily life, so whether it be a coffee filter or an air filter or something similar. And so the basic idea here is the same as that, in that we're stopping unwanted things from going through some barrier while other desired things are allowed to pass through. So let's define what we mean by filter in terms of our circuits class. So our filter is just going to be a circuit that is allowing desired signals to pass through while blocking signals that we don't want to get through. So a circuit that is designed to pass signals with desired frequencies. So we see what we're filtering on is going to be based on frequencies here. And it's going to reject signals with unwanted frequencies. So it's actually going to reject or attenuate, and so attenuate is basically just to make smaller. So sort of think about that as the opposite of an amplifier. So instead of increasing the signal, we're decreasing it. But ultimately, for these ideal filters, we're going to look at just either passing signals with desired frequencies or rejecting signals with undesired frequencies. And so we can take a step back and ask ourselves, well, why would we want to do something like this? And so as I've mentioned, I think in the past, we can think about TV and radio and anything like this that's receiving a signal via wireless means, because what we have going on is at any given time around us in the atmosphere, we have all of these signals going around, but we need to be able to pull the ones we want out of that sort of mess of all these different signals. And so in order to do that, we can utilize filters. And so you're going to talk a lot more about this idea of selecting different signals and the most efficient way to utilize sort of the space in our atmosphere to broadcast as possible in communication systems next semester. But here we're just going to look at sort of a more rough idea of how do we do some basic filtering. So starting with our ideal filters, let's look at our four basic sort of topologies here. So we're not considering any circuits yet. We're just saying we have some circuit, it's doing something, and this is the result. So notice in these plots, what we're looking at is we're looking at the magnitude of our transfer function versus our frequency. And so what you'll note in all of these plots is we have either a 1 for the magnitude of our transfer function, which would indicate that the signal is just multiplied by 1 as it goes to the output. So up here in general, we can have our output, if we have y of s, is the output of some system. We know that's going to be equal to our transfer function times x of s, which is the input of the function. So if h is 1, we're just saying it gets passed through. And if h is 0, we're saying it gets blocked. And so that's going to be true for all of these four ideal filters we're going to look at. So in the top left here, we see our low pass filter, or I suppose right now just the left. And what we can see is this blue area, this shaded region, represents what we call our pass band. And so what that means is that if any signal has a frequency below this cutoff frequency of omega c, then it's going to be passed. If the frequency is above omega c, then our h of j omega is 0. So looking from this equation, we see that means our output is going to be 0, and effectively the signal has been blocked. So what we can say here is that above this omega c, we have what's called a stop band. And so this is just some terminology. And so again, I mentioned it briefly before, but this omega c is typically called our cutoff frequency. You might also hear it called the roll-off frequency, and we'll see why that is in our next video when we're talking about passive filters. Okay, so that's our low pass. So our high pass, we have just the opposite behavior. So we can see for some frequencies below some cutoff frequency omega c, and this isn't necessarily the same omega c that we have for our low pass. This is just some variable. And below that frequency, our signals are being blocked because our transfer function magnitude is 0. But if we're above that cutoff frequency omega c, our transfer function magnitude is 1. So now our signal is being passed through without attenuation. So this would be our high pass filter. And again, the shaded blue area is going to be a pass band, and where there's not shaded blue, that's going to be a stop band. So our two other types of filters are our band pass, which we see on the left here. And so note now, instead of just one key frequency omega c, we have two key frequencies, omega 1 and omega 2. And so these are oftentimes called our corner frequencies. And so we'll come back and talk about that a little more later. So these are our corner frequencies. And so we can see why this is called a band pass, because now we have a region defined between omega 1 and omega 2 where our transfer function has a magnitude of 1, so things are being passed within this band of frequencies, so band pass, but anything below omega 1 or above omega 2 is being blocked. So then our final one is our band stop, or sometimes you'll hear it called band reject, and then another name for it is also a notch filter. And so we see the behavior is just the opposite of our band pass. We still have these frequencies omega 1 and omega 2. Again, they're not necessarily the same as this omega 1 and omega 2. And for frequencies below omega 1, we're passing the signal. For frequencies above omega 2, we're passing the signal. But any frequencies that fall between these two corner frequencies are getting blocked. So we're stopping frequencies within this band between omega 2 and omega 1, or we're rejecting frequencies within this band. So that's sort of our four basic filter structures. Again, these are ideal. We're going to see how that differs a little bit with our real filters in following videos. And we're going to, again, just as a reminder, we're going to consider two general types of filters in this class. We're going to consider passive filters using only passive elements. And we're also going to consider active filters. So we're going to bring in op amps and see how they can help us provide some advantages. And we'll talk about pros and cons of the two different styles. One other thing I want to note here is with these omega c values, these omega 1, omega 2, so let's call these just our key frequency. So let's say our key omega values are just going to be set by circuit elements. And so we'll see that as we do analysis. So essentially what that means is by choosing certain values for, if we're talking about a passive filter, capacitors, inductors, and resistors, we can determine where these cutoff frequencies or corner frequencies are.